Hello and welcome to In Control, the first podcast on control theory. Here we discuss the science of feedback, decision-making, artificial intelligence, and much more. I'm your host, Alberto Padoan, live from our recording studio in Zurich. Quick thanks to our sponsor, the National Centre of Competence in Research on Dependable Ubiquitous Automation and the International Federation of Automatic Control. Our guest today is again Tryphon Georgiou, distinguished professor at the University of California, Irvine. Welcome to the show, Tryphon.
Thank you, Alberto. Thank you very much. It's a pleasure.
So in the first episode, we haven't even touched upon the follow-up of your work with Malcolm, another Axel B. Award on the transactions on automatic control for the paper 1999 Robustness Analysis on Nonlinear Feedback Systems, an Input-Output Approach. I think this would deserve a very long discussion, but I will confine it and just say that you push forward the idea of using the gap metric for input-output analysis and design, but also towards nonlinear systems.
Towards nonlinear systems. And that paper also it generalizes the gap in many directions. You're talking of systems that are described by in different ways, very much the framework that Eduardo was following and some other, then opens up the possibility of using Banach spaces for inputs, outputs. Of course, the computational aspects there are becoming a little bit more difficult, but conceptually, the idea that stabilization is basically a transversality between the graph of the plant and the graph of the controller is carried through. Robustness has to do with the aperture between the two, the angle between the two, and that in principle you can do design. However, for nonlinear systems, it's far more difficult.
And you have many examples, though, where you apply those tools.
We have examples that include time delays and some other things.
Saturations, relaxation oscillators.
Right, yes. We were also interested in robustness of oscillations. Like, for example, in oscillations, you perturb a little bit, and then the question is at what point this oscillatory phenomenon disappears. When do you have, can you capture it again in terms of some sort of a geometric ways?
Yeah, I have a sweet spot for that, so it's easy to convince me. But my intention was to actually, I'm not going to do justice to that paper just because I want to touch on wildly different topics that have occupied your later years.
Yes.
So same year, 1999, you publish the paper called The Interpolation Problem with a Degree Constraint, basically following up on the work of Chris Burns on the subject. So he was after complete parametrization of solutions of the Nevanlinna peak character theory problem. And he is using a positivity constraint on trigonometric polynomials that was probably unnecessary, at least as you argue.
Yes. Yeah. Again, the story of this work and this sort of contribution starts in my thesis. The thesis gives a parametrization, or at least gives the existence, not the uniqueness in full generality, of a nice parametrization for certain constrained problems.
Yes.
Okay. Now, those constrained problems can be cast. You can transfer the whole framework to H-infinite interpolation. And there was a paper that I wrote in 1987, I believe, in the Science Journal of Mathematical Analysis. And the title of it is something like a topological proof of Nevanlinna peak interpolation. So that basically gives the framework of how you extend the theory to Nevanlinna peak.
Yeah.
At the time, I couldn't prove in full generality uniqueness. Anders and Chris and Gusev and Matviv completed that for the trigonometric moment problem. And then I came in showing that basically it's the same thing for the Nevanlinna peak, and then we joined forces together. Then we wrote a number of papers, basically playing exactly on the same theme. The theme is you have data and you want to have some sort of minimal realization, minimum degree, let's say filter. The natural class of filters are of a certain specific degree, and then you have a choice to make. And the choice is exactly your spectral zero, something about the spectrum, which could be used as a prior. So we use that in the context of spectral analysis for high resolution spectral analysis. That's a whole story by itself.
Yes.
But the mathematical follow-up of this whole sort of edifice is a paper that we wrote, Chris, Anders, myself, and Sasha Megretsky. And this is basically a continuation of the paper in mathematical analysis that I wrote. It's exactly that framework, but in infinite dimensions. So, and we wanted to basically redo the Saracen-Nash-Foyas commutant lifting theorem with constraint. So we chose as a title of this paper exactly the title of Saracen's original paper, H infinity interpolation H infinity with complexity constraint. And we give basically the theory at the level of the commutant lifting theorem, adding this extra sort of feature that you can actually stratify your solutions according to the complexity, which is now no longer a degree, but it's some sort of dimension of what's called a coinvariant subspace. This is like the remainder space that I mentioned earlier. But now, because infinite dimensional, it's more difficult to capture. So this is a purely mathematical paper, appeared in the Transactions of American Math Society. And in fact, it was reviewed by Saracen.
Oh, wow. It's incredible also,
Donald Saracen, yeah.
Path dependence almost. So, like the fact that you had, all the tools that you needed based on the path that you had taken.
It's actually a stroke of luck that even the work that I was doing, algebraic system theory, helped me, it's this, I mentioned the remainder space. This helped me understand the operator model of Nash-Foyas. Then it helped me sort of transition and look at it from a geometric viewpoint, the robustness theory and all. And somehow everything tied together.
Yeah, this brings back to my memory a quote that I noted down in your People in Control interview on the Control Systems magazine, where you say, everything relates to everything else.
Yes.
So, and this is something that piece of advice to give it to your students.
Yes, absolutely.
It will be a question that I'm asking you later. So let's gliss over this subject and maybe go back to the question of Nevanlinna peak interpolation, because this is actually in 2001 culminating in another Axel B award that you win with the third that you win with Chris Burns and Anders Lindqvist. The title of the paper is A Generalized Entropy Criterion for Nevanlinna Peak Interpolation, a convex optimization approach to certain problems in systems and control.
Yes.
What is the outcome of that paper?
So this is basically, again, it fits into this narrative of trying to solve interpolation problems with a complexity constraint, with a degree constraint. And the idea is that, and it turns out, again, it's a stroke of luck, that you have the relative entropy that if you use it properly, it allows you to prove most of the things we are looking at. In other words, you have now a convex optimization. So you would like to minimize sort of some norm because this is your performance criteria. And at the same time, you can put a regularizer term, which is some entropy, relative entropy criterion, which basically gives you solutions. You see, what is the relative entropy? Relative entropy has some sort of a logarithm in there. So when you try to minimize, you take derivatives, the logarithm becomes 1 over. And then the constraint comes with Lagrange multipliers, and then somehow magically the whole thing becomes rational. Because if your constraints are rational and you put in the regularizer with a logarithm, it allows you to stratify rational solutions nicely. And it kind of added to the previous work that we did. And that paper is more geared towards design.
Yeah, because then you actually follow up with many applications actually of this theory in the years to come, basically.
We had few more papers because there was also alternative approaches to constraining the degree. If I remember correctly, it was Bob Skelton had some things good using LMIs, and Abkarian and some other people. But again, everything has some shortcomings. Again, I'm not advertising it as this being panacea. It
Sure.
gives you a way to go if you would like to restrict the complexity of, in fact, not the controller, but the input to error map.
Mm-hmm.
In other words, when you close the loop, you would like your response, whatever you see, to be simple. The controller could be a little bit more complicated, but what you're going to see at the end, the response of your system should be lower order, as much as possible.
And these are applications to, you have 3 applications in the paper on sensitivity minimization, maximal power transfer in circuits,
And
spectral estimation, of course, which is an evergreen, I guess, in your research endeavors.
There was considerable work on that. One of the things, this framework that allows you to sort of select among all possible admissible spectra, a particular one, became also a theme in some other work that I did in looking at multivariable spectra and trying to be able to do techniques that have a higher resolution than what was at the time sort of the standard.
Yeah, in fact, this brings me maybe to the next subject because it is related. So I'm jumping forward to 2007, and when you start talking about distances and metrics between power spectra, so spectral density functions.
Yes.
I guess the question is, how does one compare power spectra in the first place? Because those are...
Yes, that's an interesting question. And again, I don't want to pretend that I have the ultimate answer. So I, at the time, actually, I gave a plenary at the CDC, and I chose, I forget the title, I think it was metrics, the role of metrics in design, or I forget now. It's been quite some time.
The meaning of distances in spectral analysis.
The meaning of distance in spectral analysis, yes. So I tried to explain exactly the angle I was approaching this. And what struck me, because during my early years, I had a leg on robust control and control theory, and also another one in spectral analysis, because my thesis work had natural applications there. So what struck me is that most of the culture at the time in spectral analysis was comparing algorithms on specific examples. So you would say that my algorithm is better than yours because it can resolve these 2 sinusoids. Mm-hmm. But what if there's a third sinusoid? So there was no objective measure of comparing. There was no objective measure of quantifying resolution. Mm-hmm. So I came to that, and of course, after having done also the work on the gap metric, I was very sensitive about metrics. So I tried to find out what is a natural way of doing this, and I had some proposals which are there, and they are very reasonable. So let me draw an analogy with the gap metric. In trying to compare objects, you have to decide you're comparing it with respect to what. Mm-hmm. So, for example, in the gap metric, of course, we can connect to robustness and control and so forth. But basically, we're playing a game. You generate input-output pairs for your plant, and I'm trying to mimic them. Yep. And if I can get close to what you generate, then the 2 plants are the same. Yep. So in a very similar manner, when you have, let's say, 2 power spectra, you can try to play a very similar game. You can say, I design a predictor for the time series for my power spectrum, for the time series that corresponds to my power spectrum, and I can do the same for mine. And somehow now we play a game to see if my predictor works for your time series and your predictor works for my time series. So in other words, in the context of prediction theory, you can define a very nice metric. So in other words, you try to see knowledge. So you have 2 power spectra, 2 time series, and you try to see how the performance in terms of prediction degrades if I make the wrong assumption. If I design my predictor based on my filter based on one time series and apply it on the other. So the metric captures the degradation of predictive efficiency. And then you can ask the question, so why prediction going forward in time? You can talk about prediction going backwards in time. Or you can talk about performance in smoothing. And you can do all this and you get different metrics. So you have a zoo of metrics. And, you pick the one that relates more to the application that you have in mind. And so that was a theme that I tried to develop. And
I think the most fascinating aspect of this line of research is the geometry behind this. So the fact that basically, the way I understand it is that the shape, in fact, of these power spectra is actually what matters most.
Yes.
These are positive quantities also.
Yes.
So,
exactly.
There is a very specific geometry behind this.
Exactly. Yes. By the way, now that you mentioned this actually helped me transition to optimal mass transport.
Which is something that it's the next step in my agenda, precisely, because I was wondering whether this was your first encounter with optimal mass transport.
In a way, yes. I became very sensitive to this issue of how, if you have some features in your power spectrum, you cannot just simply subtract power spectrum and integrate, right? Or you can do a logarithmic transformation of some sort and integrate that. You need some weak continuity with respect to something. Like, in other words, you make measurements and you need to know that small perturbations have small effects.
Yeah.
And it's quite natural to bring in the transportation metric. In other words, the peak of your power spectrum, how far is it from another peak?
So that was your first encounter with
that was the first encounter. I became sensitive to this concept of weighing
optimal mass transfer.
Yes.
So in fact, now we are at least in time located in 2007. We're jumping way forward, 2016 now, to your latest Axelby Award, but it's just a summary of a long endeavor in the field of optimal mass transport that you co-developed with Yongxin Chen and Michele Pavon. So the title of this paper is Optimal Steering of a Linear Stochastic System to a Final Probability Distribution Part 1, but I guess the subject of optimal mass transport goes beyond that, and given your endeavors there.
Yes.
So can you tell us a bit about what has fascinated you in this subject, and what did you, together with Yongxin Chen and Michele Pavon, developed?
Yes. It's actually, again, another long story.
I know it's very long.
starts quite a bit before that. It starts around, I think, 2005. I think it was then that there was a Mittag-Leffler program in control. And I visited there for actually 2 periods, 1 month at a time. At one time, I was sharing a place with Sasha Megretsky, and that culminated in our paper that I mentioned earlier, the one related to Saracen. And the other time I shared this living space with Michele Pavon. So
it's good to share an office with you.
Exactly. It was not office. It was actually a very beautiful setting.
Okay.
The Mittag-Leffler Institute. Mittag-Leffler, I don't know, maybe the audience, they don't know much about him. He was a great mathematician. He lived at the beginning of the 20th century. He was very rich. His wife actually was rich. They didn't have kids. And they left their property to the Swedish Mathematical Society. And they hold programs there. So there's a tower up on a hill. And all around there are beautiful little houses with 2 rooms and shared facilities.
Okay.
And people who visit there, they stay. And you socialize, talk science all day long.
Michele was your flatmate for
exactly. One time it was Michele, the other time was Sasha. So at that time, I shared flat with Michele Pavon, and he was interested he was one of the people that spent some time thinking about the subject of Schrödinger bridges. Schrödinger bridges goes back to some ideas of Erwin Schrödinger in 1932. There were very few people, some physicists, that were sort of in command of the subject, and they were very interested. And that kind of led to a lot of subsequent work in connection with stochastic control, optimal transport, and so forth. So let me explain what Schrödinger bridges are. Erwin Schrödinger, after he introduced Schrödinger equation to quantum mechanics, he was never quite convinced about the nature of it because it's very abstract. And he always wanted to get sort of a physical, understandable model for it. So in 1932, he wrote a very interesting paper. And the title of the paper was something about reversibility of time in physical laws, which touches again the things we talked before. And interestingly, Kolmogorov wrote a very similar paper with a similar title a few years later.
And they were, of course, not able to communicate with each other?
I think there was some influence.
Okay.
There was some influence. But anyway, so he was interested about reversibility of time in physical laws, why most laws in nature are time symmetric. Mm-hmm. So he was interested also about thermodynamics in some ways implicitly in this work. So he asked the following question. He said, suppose I take particles that are, let's say, diffusive particles, let's say oxygen molecules, and I release them inside the room. And they have an initial distribution. I open a box and they're all here. And they diffuse in the room and I measure them 5 minutes later and they are somewhere. The place I find them, it's a very unlikely place. So they don't have the right to be there, but somehow that's where I measured them. They should have been all over the room. So he asked the question, he said, how did they go from here to there? Now, this is a very deep question. This question relates to large deviation theory, relates to likelihood estimation, and these are both subjects that were not developed at the time. So Schrödinger had no right to pose the question, let alone answer it, and he did both.
Wow.
So the answer that he came up with is that he put down a system of equations that have to be satisfied, that if you solve them, then you will be able to track somehow the cloud of particles that move from one initial position to the other. He couldn't prove it. In order to do that, he basically managed to get the likelihood function, which is a rate function in large deviation theory that quantifies the likelihood of a rare event. And this likelihood function is the Kullback-Leibler divergence, the relative entropy. This is years before Kullback-Leibler. This is years before son of a Kramer that founded large deviation theory. And he did it all.
Incredible.
So he writes it down. He writes down Lagrange multipliers. He writes the optimization problem. He finds the shape of the optimizers. Then he writes two equations, one forward in time and the other backwards in time, coupled conditions. And he says this should be right because it makes physical sense. A few years later, Robert Fortet showed the existence of solutions for the Schrödinger system. And basically, he wanted to get the structure of the solution. So fast forward to today, I can explain this as one being a Fokker-Planck equation and the other Hamilton-Jacobi. And then the solution in between is a product of two solutions that you get from these two sort of operations, going forward and backwards. And this has great similarity with the model in quantum mechanics, where the probability of finding a particle is the square of the wave function. The square is the product of the wave function times its complex conjugate. Here you have the product of two functions. They're not complex conjugates of each other, but they're very reminiscent. So he wanted to have this as a model to explain quantum mechanics. The subject developed very slowly for 50 years, and it was properly understood in the 80s as a large deviations problem. There was a fellow Fulmer, and then Nelson at Princeton tried to develop quantum theory based on that, and the subject was called stochastic mechanics. It was kind of an esoteric subject, very few people knew about it. And Michele came to know these people, and he was studying it, and he wrote a couple of papers in the 90s. But again, it was focused on a very, very specific setting. So at the time we were sharing a flat, he tried to explain me what Schrödinger bridges were. So Schrödinger bridges is basically to reconcile the prior law, which is, let's say, Brownian diffusion, with the very unlikely marginals that you measure at 2 points in time.
With the observations, basically.
With the observations. Mm-hmm. If you like, this is again a moment problem. Truly, it is a moment problem because you have again a relative entropy that you try to reconcile with measurements. So everything kind of fits together. So then slowly I started realizing the significance of this in the context of control, because this is the way it was posed by Schrödinger was an estimation problem. But it turns out, and this was something that was brought to the picture by a student of Michele Pavon's in the 90s, Dörfler. So if you write the likelihood function, then there's something called Girsano's theorem, which allows you to see that the optimizer, the most likely path, turns out to be minimizer of a certain functional, and this functional can be interpreted as a control. So in other words, you have now a problem to reconcile two marginals with a prior law, and you can find the most likely thing that happened between. The most likely thing that happened between is the least energy path that the particles would have taken if they were under your control.
Amazing.
So all of a sudden, this is both a control problem and an estimation problem. Both things go together. So then I was visiting Michele in Padova, and we wanted to work on this more. And we started almost from, how can I say, almost the opposite end. Because at the time, we hadn't quite fully realized the significance for control, and wanted to extend kind of the framework of Schrödinger bridges. And we thought of extending it to fully quantum mechanics. So in other words, the marginals be density matrices of a quantum system, and to see if in the setting of quantum evolutions you can do something. So we wrote a first paper on that. I think it came out in some physics journal. And it was just sort of an experimental thing for us, but it actually led to a generalization of the theory to something that was not conceived at the very beginning. You know, it was almost like, again, that's a very long story, and something that is not finished completely. Mm-hmm. Then I was back at Minneapolis, and I was thinking about the possible connections to control. And I had, as a student, Yongxin Chen, who was, it was a great stroke of luck that he came to work with me, a very brilliant young man, absolutely brilliant and a wonderful person. So at the time, very early on, I'll fast forward to that point when Yongxin came, I decided initially to give him something to sort of, and I described to him, I said, look, this was not Schrödinger bridges. And I said, I'll give you a problem which is very technical, and it's almost like weightlifting. You go to the gym, you exercise before you take on something different. And I gave him something about, now this is, I don't want to go on a tangent, but a very interesting technical problem on filtering and smoothing and estimation. And this we completed with Johan Carlson, another person that I worked with. At the time, he was a student of Anders Lindquist, and he was visiting me there early on and so forth. It's another dimension of this collaboration. Some beautiful work came out of that. And Johan actually was in one of the key papers in bringing optimal transport into power spectral estimation. So anyway, then after Yongxin worked on this technical problem, I realized that he has a great potential. He was absolutely superb. He would master a subject very quickly. He was very creative. So at the time, I thought something long-term for his thesis and looked at a baby version of the Schrödinger bridge problem. So we wrote a small short paper for the transactions, and then realized that this relates very much to quadratic regulator theory of a different kind. And at that point, we started also working with Michele, and we wrote that first paper that was basically to steer distributions of stochastic systems for some initial to some final. And in that paper, it became very apparent that the Schrödinger system, the forward-backward, is exactly a Fokker-Planck and a Hamilton-Jacobi. And to solve this, the moment you have your setting to be linear quadratic, in other words, linear systems, Gaussian processes, then both of those become Riccati equations. So you have a forward and a backward, and they are coupled through the boundary conditions. So it's a non-standard problem that for the particular case where you have a certain type of structure that the noise, the process noise enters through the same channels as the control, it can be solved closed form. So you can write down a closed form solution to what problem? So here is the problem. You have a stochastic system. It starts from some initial distribution, and you would like at the end of the interval to reach a particular target state, and the state is a distribution. Traditionally, optimal control, linear quadratic regulator theory puts a cost at the terminal stage, and the distribution at the end is a consequence of your cost. So you have to fiddle with your cost to get something acceptable. Here you can exactly decide on the terminal distribution, and you design your control to reach exactly that. Mm-hmm. So you don't worry about the cost. You solve exactly for the target distribution that you want. Now, there are subsequent papers that relax certain constraints that we had. For example, the key constraint is that the noise process and the control enter to the same channel. So we relax that in paper 2, part 2. And then we have part 3, and there's also part 4, which we have it kind of in the works for years now, but we want to add more to it.
I mean, related to this line of research, one paper that I really enjoyed personally was Stochastic Control Liaison. Richard Sinkhorn meets Gaspar Monge on a Schrödinger bridge. Really a delightful paper. Pretty long, I must admit, but the whole story is very entertaining to read.
Right. We try to tell the story of how Schrödinger started with his ideas in 1932.
Yeah.
Sinkhorn came much later. Sinkhorn solves a simple baby version of the problem for matrices. Mm-hmm. But the algorithm for solving such problem came to be known as a Sinkhorn iteration.
Yeah, maybe we should clarify for the audience what is a Sinkhorn iteration.
Yes. So the Sinkhorn problem came initially as a hack in statistics. So in statistics, let's say you have two random variables, A and B, and you know a lot of things about their statistics, but you know very little about their joint distribution. So you have a prior on the joint. So you know that if the random variable 1 takes this value, there's a chance that this other, But the joint is not, the joint you have, the prior, is not consistent with the marginals. So now you like to update the joint to be consistent with the marginals. In very simple terms, you have a matrix of positive entries, and you would like the row sum to be equal to something and the column sum to be equal to something else. And they're not. So what are you going to do? So what they did is the following. They take the matrix, they take the row sum, they don't agree with what you're given. So you multiply the rows by a suitable scaling to make it right. Then you look at the column sum and you do the same. They don't agree with your data, so you adjust them and you keep doing that. And they observe that this converges. So they started using it, and then later on Sinkhorn proved that indeed it converges. So he had the technical proof. This is a baby version of the forward and backward of the Schrödinger system. And this is a baby version of Robert Fortet's proof, which is in the same thing happening in path spaces for particles. So the whole thing ties together.
It also shows the connection to Kantorovich problem.
To the Kantorovich problem, exactly. The Kantorovich problem has to do with deciding on the joint distribution that is in agreement with the marginals, but now you have a joint that you choose to minimize a certain other functional. And that is the optimal transport problem. Yeah. So the two problems kind of fit together. Yeah. And one can say that the Schrödinger is the regularization of the optimal transport. So the optimal transport problem is simply the problem of moving mass from one point to another.
Yeah.
And then you say, what's the optimal way of doing this? So you have an optimization criteria. So for example, you can think of it as an initial distribution of a dynamical system and a terminal distribution. Mm-hmm. And then you have dynamics. Let's say, for example, x dot is equal to u, right? And you want to minimize the control effort. You minimize integral u squared, for example. That is a form of optimal control and optimal transport. Now, if the system is subject to stochastic excitation, then that is now the Schrödinger problem. So again, these two themes are interlinked in so many different ways.
And control plays a huge role.
Control plays a huge role. These are exactly control problems.
So one, I imagine, can start posing all control theoretic questions in this framework.
In this framework, yes. Yeah. Yes. You have a cost. We are very familiar with minimizing costs, and you have a likelihood function because some parts of your system are uncertain. So when you bring those two things together, that's exactly that kind of framework. And the beauty about this framework is that it gives you some nice geometry in the space of probabilities. If it was just an optimization problem, it would be an optimization problem that we develop some tools and we press carriage return and we get an answer. It's more than that. It allows you to think of the flow of densities in some abstract manifold, which is infinite dimensional. And this abstract manifold is essentially a Riemannian manifold. So you look at geodesics and you look at all the stuff that we're familiar in finite dimensional spaces become infinite dimensional. So the flow of uncertainty of your system is a path in this space of measures.
That's amazing. I guess you're referring to techniques that arise in Wasserstein.
In Wasserstein. This is called Wasserstein geometry. Yes.
Geometry, yeah.
And it's control. If you look at it, it's control.
That's amazing.
There are beautiful contributions there. There are some names that without them, this subject wouldn't exist. Benamou, Brenier, and Macan, and Gangbo, and Otto, and Villani, and several others. The subject started developing in mathematics with strong connections in probability theory, and the control aspect, of course, was not there. But, after, we were very lucky to be very early on.
I mean, more than one Fields Medal has been awarded very recently to the subject, so it's a very active field.
Exactly.
My question here would be, okay, where to bifurcate? Because according to my agenda, I have, in the same year, 2016, a paper called The Color of Turbulence, which I found incredibly interesting. But also, we could branch off towards thermodynamics because there's strong ties between, what we just talked about.
Absolutely.
So I'll let you choose.
It's a hard choice. Before we started this conversation, I thought it's going to last for half an hour or an hour. See, here there's in fact a lot to be said. So let me say one thing about The Color of Turbulence. This is work with Mihailo Jovanovic. It's quite an interesting thing. The word color of turbulence, it was a pun.
Yes.
And we sent it to Journal of Fluids and thought, they would be unhappy. But actually, they loved it. So this ties up, and I'm not going to say very much on this, it ties up with the work on estimation, on power spectra, and some other work on inverse problems I was doing in early 2000. And those problems have to do with the following. You have some dynamics, and you're observing certain statistical behavior. Think of a dynamical system and think of the output of the system that is a time series. And you're observing it, you know the statistics of it. Now, but you know the system. So you ask the question, what is the input that caused the observed behavior? And you can get a lot of information about the input. It's an inverse problem. This relates to antenna rates, relates to a number of things. The work with Mihailo came because of his interest in fluids and developing tools for control of fluid flows. The problem there is that you have Navier-Stokes and they're very difficult to handle. So if you have linearized Navier-Stokes, they're easier to handle. The problem is that they cannot replicate velocity fluctuations in turbulent flow fields. So then in talking about possibly looking at it from different angles, we came up with the idea of taking the Navier-Stokes linearized and seeking a stochastic excitation that makes the observed behavior consistent with the dynamics. And so it turns out that the stochastic excitation has to be colored in order to produce the statistics of velocity fluctuations in turbulent flow fields. And that's why exactly we put the word the color of turbulence. In other words, what color you need in order with the linearized dynamics you generate statistics which are consistent with the physics. And you get a lot of insights from that. So that closes kind of the subject.
I just want to mention to the audience what color actually means in this context, because some people may not be familiar. Color essentially has to do with basically the
frequency. If you have a time series, it has a power spectrum. Power spectrum means sort of the power that is at different frequency bands. So high frequencies are ultraviolet, low frequencies are infrared. So it's an analogy with the visual spectrum.
Yeah.
So
white noise as well.
White noise indicates that you have the same power at all frequencies.
Exactly.
Where if it's colored means that some frequencies have more preference than others.
Yes.
So this is and again it was a pun, but there was a real sort of intuition behind this.
Definitely.
Yeah,
I just wanted to ask you, it seems like this circle of ideas for you in these years really gravitate you towards thermodynamics in a certain sense. It projected you into that direction.
Yes, this is true. In fact, there were also earlier instances that some of the ideas came and of course I was influenced by reading physics literature and also some of the giants in our field, including, let's say, Jan Willems, we talked earlier, and Roger Brockett, were also interested in thermodynamics going far back and the connection with stochastic control. So somehow the ideas encircling the subject of optimal transport and Schrödinger bridges come very handy to start looking at thermodynamic systems as evolving on exactly this manifold of distributions. So what is the state of the thermodynamic system is the probability distribution of the state of the system. Because you can think of it as particles that are stochastically driven, and you're controlling them with some potential. So you squeeze the potential and you bring them in line. By the way, the subject we're talking right now, stochastic thermodynamics, we're going to go into, the father of it is Einstein. Much of what we're saying now goes back to 1905. And it's truly remarkable. You look at this, you look at what Schrödinger did. You look at the papers of Einstein, the clarity of it, how far ahead they project. And it takes us like 50 years to understand Schrödinger. It takes us, another, I don't know how many years to understand the contribution of Einstein. So Einstein, in this paper, he has this famous relation, has the diffusion coefficient related to fluctuations. So basically you have a stochastic excitation of particles inside a medium. So he says, suppose, let's say, I'm just simplifying it. You have this particle and you tie a rope into it and you start pulling it. So if you start pulling it, you're going to feel the headwind from other particles bombarding onto it. So the force, which has to do with dissipation, relates to the fluctuation of the particle, how it moves about as a Brownian particle if you don't tie the rope to it and you let it on its own.
Okay.
So there are two different phenomena that are coupled in this paper of Einstein. He just saw it, that this is a model for it. And this model is absolutely ideal for thermodynamics. Fast forward in about 1999, and you have another beautiful paper by Jordan, Kindler, and Noto. And they were interested in speed of convergence of the Fokker-Planck equation. And they show that the Fokker-Planck equation is a gradient flow of the entropy functional in the Wasserstein space. I know this is very fast.
No, it is fast, but it's also super fascinating. It's quite incredible, actually.
So those two things put the substrate for what came to be known as stochastic thermodynamics. Stochastic thermodynamics started in the late 90s. People started thinking of small ensembles of particles and random fluctuations. How do you quantify random fluctuations and the likelihood of certain event? And it started shaping up more and more as we go into 2000, 2010, and so forth. And somehow we came with very fitting tools at about the same time, and we looked at the control of stochastic systems and thermodynamic systems from a control perspective. So imagine now that you have a bunch of stochastic particles inside some potential, which is basically the same thing as if you have, let's say, a cylinder and a piston, and you have molecules, air molecules in there. So closing the piston is like constricting the potential. And the Carnot cycle is you just heat it up, you let the piston go out, you cool it, you push the piston back, and you get some work out of that. And Carnot, many years ago, was absolutely brilliant. A guy in his 30s writes a single monograph, which he publishes by himself, with this idea of, that led to the Carnot cycle and transformed the field, talking about Carnot efficiency. But up until the year 2000, and even later, actually no, a little bit earlier, the statistical thermodynamics was not able to answer the simple question of saying how much power can you get through a Carnot cycle.
Wow.
Because the Carnot cycle is quasi-static. Quasi-static means it takes you infinite amount of time. So you divide by the time, you get zero power. If you start moving faster, you say, I'm going to do it in 1 minute, go back and forth. You cannot quantify dissipation and losses. So dissipation and losses start being possible to come to the picture with stochastic control. And this start materializing around the year 2000 moving forward. There were ideas going back then. So we come into the picture with the right tools, and we start looking at this, of how much power you can get out of engines. Initially, we're looking at the thermodynamic model of Carnot, but later on we come closer to, again, this is going to be fast. But it's a really absolutely beautiful subject. When we look at engines, we don't want to look at engines that you put in your car, clearly. One is interested also how, for example, cells generate power. There is a very well-known mechanism of nano engines, which is the bacterium flagellum. The bacterial flagellum is an appendage which spins at thousands RPM. And bacteria can swim something like 17 body lengths per second. It's amazing. Imagine Mark Spitz swimming that fast. The question is, how do they generate this power? So the way nature generates power is not the Carnot setting that you bring the thermodynamic system in contact with a cold and a hot heat bath. The way you do it is you bring the thermodynamic ensemble in contact with the cold and the hot at the same time.
Okay.
Imagine in this room that one wall is very hot and the other is very cold. What is going to happen? You're going to see a tornado.
Yeah.
So the air will start circulating, getting some energy from the hot wall and delivering to the cold wall. And at the same time, you get sort of this vorticity. So if you sit there in the middle, you can put a little sail and you can get a torque out of that.
Okay.
So that's exactly how the biological cells genetic work. You have a gradient of something, temperature gradient, or you have chemical gradients. You have chemical potential gradients. So, and then you have a system inside that has more than 1 degree of freedom. It's a system. It's a dynamical system. The dynamical system is excited by different sources of noise. And the noise flows through the system from one part to the other. And then you're there to control the system and adjust so that you get power out of it. There is a beautiful principle which is basically exactly out of textbook. And we wrote a little paper on that with my students. on impedance matching for thermodynamic systems. In order to get power out of this, sort of the gradient in conjunction with the state dynamics creates a torque. How much torque you have to apply in reverse so that you are driven and you get power out of it? Exactly half of what the system can produce. Because if you apply exactly the same, the engine will stall and you get no power. If you apply zero torque, it will spin very fast and we get zero power. It's exactly half. This is, in circuit theory, is called impedance matching. So you need to match the resistance of the internal resistance to the load. And there's the same principle at the level of stochastic control. So we studied exactly the maximum power you can get out of thermodynamic ensembles that work in this anisotropic field. Anisotropy means you have a gradient. The gradient is steering you. It's steering the pot. And then you sit there in the middle and you get some torque out of that. This is called gyration. Mm-hmm. And it goes back to ideas of Richard Feynman. You know, how you get work out of a temperature. You know, if you need two temperatures. There's no way you can get out of one temperature.
Yes.
And there's all this discussion, philosophical and otherwise, starting from Maxwell and Boltzmann and, you know, whether you can get a perpetual motion. Of course you cannot, but how much you get if you have some temperature gradient or chemical gradient. And there's a huge number of control problems. Like, for example, you have, let's say, you have a temperature gradient, but the temperature is not provided you by the sun. It's a limited bucket of energy. So you have finite capacity heat baths, right? Inside the cell, someone generates the chemical gradient. So it's not cost-free. You cannot just say, this is the gradient and I'm going to get work out of it. You have to be efficient. So those things have not been quantified yet.
It's quite crazy.
Yes. Like, let's say I have a finite capacity heat bath. For example, I have in this room, let's say a bucket of water that has this temperature. Mm-hmm. And I know the temperature of the room. Now, if I use optimally a way to transfer heat from here to work, and I have a limited time that I want to do this, how much work can I get?
Mm-hmm. And the enabling tools in order to quantify, can I say dissipation terms?
Dissipation terms is basically a quadratic term that basically quadratic costs mm-hmm. in exactly the control setting. It's some sort of quadratic cost.
So, okay, this is basically a venue where stochastic optimal control is
absolutely
perfectly suited.
It fits like a glove.
Okay.
So we looked at this, how you gain work out of anisotropy, and we got a very similar picture that classical thermodynamics has for quasi-stationary. Mm-hmm. But they're talking about efficiency, not power.
Okay.
So the picture we get is the following. You have the state of your system is a point in a manifold. Mm-hmm. And with control, you can regulate the state to follow a certain path. Mm-hmm. So the path is due to your control as well as the stochastic excitation. If you try to optimize, you want to optimize power you get out. What turns out to be the case is that the length of the path corresponds to dissipation, and the area enclosed corresponds to work that you get out. So you get isoperimetric inequalities to quantify the limits of what theoretically is possible to get out of this thing.
Amazing. And
it's absolutely beautiful, and it's purely controls. It's all the tools that we know and love. And it's a great journey. Somehow I can go on and on with questions about what is open. There are many, many things that you can think of. And the moment you start thinking about limited observations, limited this, limited that, it's wide open.
Yeah.
There is also Well, that's another story. I'm thinking of quantum, because I mentioned earlier that we did quantum bridges.
Yeah.
And we also tried to replicate some of the tools of optimal transport for non-commutative objects, for matrices. And these were driven by early work on the spectral estimation of multivariable processes, because you have matrices. So that's another story. I can't go into this because it's
yet another episode.
it's another episode. But in fact, this was some work with Yongxin Chen and Alan Tannenbaum.
Yeah.
And what we did is, you see, I mentioned earlier on that there was a paper by Jordan, Kindler, and Otto that they showed the Fokker-Planck equation. The Fokker-Planck equation is the gradient flow of the entropy in the Wasserstein metric, in the optimal transport metric. What does this mean? It means that if you start with a distribution, the distribution is the distribution of your states, and it has some entropy. Now you ask the question, you say, how should I modify the distribution in such a way so that I reduce the entropy, increase the entropy fastest? In order to do that, you need a metric, because you need to know the step you're going to take has to be quantified. You really need a metric. You can take any metric. You can take an L2 metric, and you can get some other things. But if you take the optimal transport metric, it turns out that the direction you move gives you some differential equation. That's a partial differential equation because you're talking about distributions. And that is the gradient flow, and that is the Fokker-Planck equation. Now, we replicated the same thing for quantum systems. We defined a non-commutative transport, and then we showed that a version of the entropy, which is called von Neumann entropy, has a gradient flow which is something called the Lindblad equation, which quantifies dissipation for open quantum systems.
Wow.
So it kind of parallels this. And this is also an interesting story because we did this work simultaneously with two other groups. All three papers were uploaded in the archive within 3 weeks.
Wow. Amazing. It means the critical mass was there.
It was a critical mass for that thing. Yeah. We were lucky to be in this very rich subject at a nice time. So some of it we're pushing, some of these other people are pushing, and it's a great amount of fun. It's just absolutely beautiful.
This is fantastic because I'm sure that many out there will be inspired by this conversation. I mean, at least this is my hope. I want to jump to the last subject of the episode, which is a paper that you wrote relatively recently with Malcolm Smith on, it's called Principles of Lossless Adjustable One-Ports.
Yes.
And I found it really fascinating. I mean, the consequences of this paper could be quite big, in my opinion. It would be nice. I mean, I would summarize it as you're asking the question whether it's possible to build a spring with an adjustable knob that basically changes the stiffness as you please, but without doing work.
Real time without doing work, yes. So that was a question. Malcolm had shifted over the years with his concept of inertia towards mechanical systems, and he was visiting me for a half sabbatical. So we're sort of toying on what to work on. And at the time, he stayed with a colleague of mine because my house in Irvine was a bit smaller in terms of having visitors. And he stayed with Faryar Jabari, a colleague of mine. And somehow we thought what to work on. And Faryar had worked on some things on changing sort of some forces, but not losslessly. He had some mechanisms, and somehow we wanted to engage also Faryar. So we thought about looking at what is possible in this direction, and this culminated in this paper. So the question is exactly what you said. You have, let's say, a spring, and you want to losslessly tweak a knob. Mm-hmm. Or you have some inertia, and you can tweak a knob. Or a capacitor, if you like.
Yes.
The problem is that if you space the plates of the capacitor further out, you need to do some work on it. So the question is, can you do it losslessly? So this is tied to being able to have a variable transformer, which is lossless. So we came up with a concept, a mechanical concept, to show that this, at least in theory, is feasible. It's very difficult to describe in words, but
well, there are nice diagrams in the paper where you show.
Yes, the gist of it is you have some ball bearings and some cones that are coupled in such a way that all the forces are perpendicular to their motions. So by moving suitable parts of this, you change the ratio without doing work. Of course, you're going to do some work because there's going to be rolling friction, etc. Nothing is perfect. But in theory, you can do it. And in fact, we built this device. We applied for a patent for it.
That's amazing.
And the preliminary things indicate that
it is possible.
It's possible and it conforms, but we need more experiments and more to validate. But of course, in theory, it's there. And in practice, it's possible. Of course, you're going to have some losses, but the losses are not intrinsic to the problem. They're because of imperfection.
Yeah, I guess I'm going to clarify a couple of things for our audience. So first of all, what does it mean to be lossless? It means without dissipating energy,
yes.
I imagine. And the other thing is that we mentioned the inerter. The inerter is a concept that Malcolm Smith came up,
yes.
I guess, in the early 2000s.
Yes.
And yeah, it's been applied in Formula One just to give people an idea about also of the impact of these ideas.
Yes. Yeah, the inerter is a brilliant idea. So Malcolm at the time was working as a consultant for Formula One. And then I'm telling you very quickly the story. And then Formula One had active suspension and he was helping them design this. And then the body overlooking Formula One decided to ban active suspension. So you was thinking what you can do with passive suspension. And there is no such thing as a capacitor for mechanical. A capacitor is basically a device that you push the two ends and the acceleration is proportional to your force. It's basically, if you have kids, they have this spinning top. You have a spinning top that you push a lever from the top and start spinning. That's exactly an inerter.
Yeah.
So if you push it, it starts spinning. And if you pull it, it slows down and spins the other way.
Yeah.
And it stores kinetic energy into the spinning. So it's like a mechanical capacitor. So the brilliant idea is to use it as a design element. The rest is history. So he developed this, and in Formula One, it gave a slight edge, which is significant, because you change the dynamical response of the tires and you get better traction. Yeah. Of course, he should be the one to explain to you. And
he's always welcome on the show, of course.
Yes.
One last thing that I want to mention in technical terms related to this paper, so the principle of lossless adjustable one-ports is, of course, in this paper you work out the mechanical version of this thing, but there's nothing that I imagine found in, let's say, applications towards the electrical, fluid, thermal domain.
Absolutely.
Right? So, yeah.
So let me say one thing. For electrical analogs, we thought long and hard. And so we have some discussion at the end, but it's based on a mechanical design. To this day, we don't have an electrical analog of the concept.
Okay.
So it's not obvious. You tend to think that this is going to be trivial. Let's say, for example, how do you get a variable transformer? Oh, no big deal. You just go to the store and I get a variac. Not so fast. The variac, you have two coils. You know what the variac is, right? You have two coils. You just have a transformer. And one of them has a variable contact point for the coil. And you say, what's the big deal? I just effortlessly moving up and down. Not so fast. When you move it, you move the contact point, it jumps between spirals of the coil. And energy is dissipated there. And in fact, there's a lot of energy dissipated there.
Okay.
This is a very little appreciated fact even in physics. I mean, many people sort of go through their curriculum and they don't realize the following thing, that sometimes certain processes, if you take the limit, you get discontinuity. Mm-hmm. So for example, here, when you move the contact point from one spiral to the next, necessarily you're going to have a spark, because you move from one voltage to another. The spark means that there's going to be current going through a very high resistance thing, and some going to be dissipation. Mm-hmm. And if you try to compute how much dissipation is significant, an example that, again, the audience, if some have some background in physics, there's a very beautiful example which you always see at the physics courses. I mean, I don't know, maybe not so much. Let's say you have two capacitors, and they're just sitting on their own, minding their own business. One of them is charged with a current, some charge Q, and the other is not. Now, there is some energy in the capacitor, and you can compute how much it is. Mm-hmm. Then you bring two wires and you connect the capacitors, so they're now the two in parallel, so the charge redistributes. And then you ask the question, how much energy do I have now in the capacitors? If you compute it, it's a very simple exercise. You have half of what you had before.
Okay, yeah.
And then you say, what happened to the other half? So the other half was lost in the connection. Mm-hmm. So when you connect, you cannot just say, I connect. You have to connect through some resistance. Mm-hmm. It doesn't matter what resistance you put. Even you put epsilon, you're going to have a very high current, small resistance, the same amount, it's invariant. Mm-hmm. By connecting in parallel, you're going to lose half of it. There's no way you can avoid this. Mm-hmm. And the same thing happens in playing with variacs and trying to make.
So the physical implementation of an electric analog.
An electric is not obvious. At least we have not been able to.
Well, the new generation is invited to read the paper.
Yes, absolutely. Because we haven't, we moved to other things and the time is only limited. So it's not, I'm sure there is something. Yeah. And it's going to be beautiful. The moment you see it, mm-hmm. it's going to be obvious. Mm-hmm. But before you see it, it's this aha moment. And we experienced it before in all these steps. And there is one moment like that sitting there, but, it's probably for someone else to discover.
Well, I mean, this brings me very nicely to the end of this episode, because we're talking about new generations. We're talking about aha moments. So I'm wondering is there anything that you would have wanted to know when you were starting your career, and any piece of advice that you could give to future generations?
I guess the thing I want to say is it's a long journey. I tell my students, the previous thing that you mentioned, that everything is connected to everything else. Look for the connections, look at similarities, and sometimes there's a great deal of satisfaction and pleasure when the fog is lifted and somehow there's a moment of clarity and you see the big picture. But that requires both work, persistence, and scholarship. You have to go back sometimes to the basis of the ideas, the basics. You read the literature far back. Sometimes you learn a lot by going, let's say, to the horse's mouth, as they say. I remember sort of in the early days when I was trying to understand interpolation theory, the clearest picture I got was by looking at works in the 50s, in the 30s, like say the work of Nehari. You look at it, and the clarity in this very short paper is amazing. And here it brings me back to another thing that I give advice to my students. Of course, it's important to have your work recognized. It's important. And nowadays, there's a lot of competition. People need to publish because, unfortunately, this is the new terrain, and you have to compete in that. But the thing that gives me the most pleasure, and I try to tell my students, I draw a lot of satisfaction knowing that something similar will happen to what I experienced when I looked at, let's say, a paper. I just mentioned Nehari, right? You look back and something that was very unclear, all of a sudden you see a little lemma which is very sharp and clarifies everything. You say, oh, that person is smart, was smart. So I tell my students the following. Years from now, when I'm gone, let's say 30 years, 40 years from now, I draw now pleasure knowing that someone will look at this paper and say, boy, this is interesting. That is a clever statement and a clever argument.
Nice.
And it's not going to affect anything I do now, but sometime, somewhere, someone will benefit by looking at this. And it brings me back to also some discussions I often have with Malcolm because we worked for so many years together. Sometimes we take pleasure out of looking at some sharpness of an argument. And in fact, some of this, I want to say this also, looking back at our papers, and also myself, they were written at a certain time, and there was a culture. And looking at them now, sometimes I look at it and I say, would I have changed anything? Maybe not, but they're not ideal for being read at all times, right? I mean, and sometimes they are very compressed. Mm-hmm. In fact, it has happened that we look at a lemma we wrote and we said, oh, is the proof complete? And it took us like 5 minutes to realize, yes, not only was complete, but we don't want to change anything. But it was short, But you have to get into the mode of understanding this with the language of the times. Mm-hmm. And then you see the picture the way it's painted. And the same thing applies now. You write something, you come up with an idea. And the moment you see this, you have to think of yourself also as a painter. You have to write it in the way that is elegant and will survive the test of time.
Yeah, a painter situated in time.
Yeah. So we are extremely privileged, everyone who is listening, to be in academia. Mm-hmm. It's sort of the best job. Sometimes I tell my students, I do what I like doing, and the interesting thing is I get money for it.
That's the secret of a happy life. Yeah. Well, I guess this is a good time to actually close this episode. Tryphon, it's been an honor and pleasure to have you on the show. Thank you so much for joining us.
Thank you very much. It has been absolute pleasure. I enjoyed it. Thank you very much.
Thank you for listening. I hope you liked the show today. If you enjoyed the podcast, please consider giving us 5 stars on Apple Podcasts, follow us on Spotify, support on Patreon or PayPal, and connect with us on social media platforms. See you next time.